Good afternoon, everyone. Welcome to my presentation. My name is Shin Yee from SpeedGo Computing. A little bit about myself. I love algorithms and I do programming for a living. I enjoy mathematics, but just not necessarily good at any of these above. I was inspired to look into UNAM Type 1. Somehow, I couldn't find a way to apply that in my algorithm design, mainly due to the variable bit size and also difficult to index one element in a multi-dimensional matrix. So now we have a new number format called the Posit. It has fixed bit size, easy to index, and it offers higher accuracy than standard floating-point numbers. So my question is whether I can use Posit to reduce the memory footprint, since the memory limitations, the bottleneck is a serious problem in many parallel systems, and whether we can use Posit to resolve the accuracy issues in my graphics rendering applications. The self-intersecting problem is very common in ray tracing, that we try to find intersections between rays and the objects. And because very likely we can't represent the points exactly in number, so it will either round up or round down. That if the point is rounded to the back of the surface and the secondary rays casted on the same point will be intersecting with the surface itself, that will cause a shadow problems. That is not desired in ray tracing. So after spending so much time on this, setting up the experiment, about the time to replace the computation with Posit, existing Posit implementations, then I get these surprising results that the multiply 3 by 4 multiplied by 5 by 7, obviously I should get at least 15, but I was getting 9.69. Another implementations, it couldn't compare the negative numbers properly. So I was stuck and I was lost for a while, and I was complaining to my friends, but the complaints wouldn't help. So instead, I was motivated to work on this current work, that is the provably correct Posit arithmetic. So I was motivated to implement a correct Posit implementation that is based on provably correct Posit arithmetic. And Professor Donald Kernoff, he's a person that can prove in paper the algorithm that is correct or efficient in paper, and nobody will question. But I'm not the same level as him, so I couldn't do the same. So in this work, I'm including the software tests and verifications. In case I didn't prove certain parts of my computation, at least I have tests to verify that I'm actually producing correct results. So our approach to this work is to use the big integer model that never overflow and the fixed point numbers that help a lot in simplifying the mathematical proofs. The big integer model simply doesn't overflow. That means if we are working with just small Posit numbers, let's say 16-bit Posit with ES equal 1, we possibly can use a native 64-bit integer for all the operations, as long as it doesn't overflow. So it need not be a very big integer. In this work, we focus on the decoded Posit. In the Posit specification, we define the binary format of the numbers. In this work, we simply implement the encoder and decoder, but we didn't prove it mathematically. So in this work, we really focus on just the Posit arithmetic of the decoded Posit. So for the Posit defines two special representations for 0 and not a real. Previously, we also called the plus minus infinity. Now we are adopting a new terminology, not a real. So for arithmetic involving any of these special numbers, the results are expected, and these are all the possible combinations. So in an implementation or even a test cases, you can just look up the table for the expected results. Let's say for a normal posit with a special zero value, the addition should return the A value. Multiplication should return 0. All these can be determined by just looking at the types of the numbers. So for normal posits, we rely on these two definitions, the posit definition and the fixed point definitions. And all the parameters in the formulas are integers. We convert posit to fixed point number. If we group down the exponent part and the non-exponent part, we can easily see the relationships. And since x should be an integer and f divided by 2 power h is a fraction, so in order to make this an integer, we multiply x with 2 power h. So we get this. So we get this formula for x and m. For converting fixed point back to posit, having this formula here as a reference, we are given x and m. We can determine s by simply looking at determine the sign of x. And since by definition f is strictly less than 2 power h, the log of absolute x will just return h. And as we know the value of h and s and also x, the value of f follows by itself. For the exponent part, e is also strictly less than 2 power es. So we can compute the value of k by using a floor division of n plus h divided by 2 power es, and the e is just a remainder. So given we converted our numbers to fixed point, now the formulations becomes much easier. By definition, we have these fixed point numbers, the two numbers. We want to perform an addition. The key is to group the key is to use a specific exponent values on two of the numbers, so that it result in a common exponent that can be factored out. After that, we do the cross multiply and move the denominator out to the exponent term. So we have our fixed point output xc and mc. The multiplication is surprisingly easier, that we just need to group the exponent part and the non-exponent part, then we get our output xc and mc. And that is the QED. If to impress your neighbors, you will tell them this is quite easily done. For division operation, it is an outlier among the four basic arithmetic operations. For addition, subtraction, and multiplication, you are able to get the result exactly represented in a posit, maybe with a longer bit size. But a division, it will produce a residue, the remainder divided by y. That in general may not be represented exactly in the posit number. So when we can't represent it exactly in the posit, we need to apply posit rounding to the nearest number. Posit rounding will round to nearest number, depending on if you are rounding the fraction bits or the exponent bits. You will have the minimum absolute difference or minimum ratio. When your value is exactly at the midpoint of two consecutive posit numbers, we break to even on a tile. That means we are rounding to a posit that has a 0 at the least significant bit. And in addition, we never round to 0 or not a real representation. For example, a posit we have sign bit, regime bit, exponent bits and fraction bits. This corresponds to specific parts or specific parameters in the formula. So let's say now we have a 16-bit posit. We would like to round this number to a 8-bit posit. So essentially, we are making a cut here. In this case, we are cutting away one exponent bit. That's the t equal 1. We are cutting away one exponent bit along with the fraction bits so that we represent our value in just 8 bits. So we have two choices. Either we round down or we round up within these 8 bits. And to round down or round up, it depends on the midpoint of these two numbers. So if we analyze the formulas of these three numbers, focusing on just the exponent part, since we are rounding the exponent bits, we can see that the midpoint corresponds to having the t bits value equal to 2 power t minus 1. In addition to the 0 fraction bits and also the remainder equals 0. So based on the value of the t bits that you are rounding up or down, you can determine whether you should round down or round up. So with these conditions, we know that our value is actually strictly less than the midpoint, so we should round down. And with these conditions, we know it is strictly greater than the midpoint. So we round up in this case. And if it is exactly at the midpoint, then we round to even. That is, we round to a positive number that has a 0 at the least significant bit. And note that we don't need to know the exact value of r in the rounding. Similarly, for rounding fraction bits, we use the comparisons of 2 power t minus 1 and the value of the t bits. We can determine whether we should round down or round up or round to even. And we don't need to know the exact value of r as well. Rounding residue, maybe you only encounter this when you are performing a division. Before that, when you are implementing the addition, subtraction, multiplication, you may not expect to round something else, the residue. So in this case, we are rounding to the same number of bits, but getting rid of the residue. So in this case, the midpoint is exactly with 2r equal to y. So we can apply the rounding using the condition test, whether 2r is less than y or equal to y or greater than y. And we need not knowing the exact value of r and y. And this leads to this result, that the residue value r and y could be very large numbers after a division. So we find that you can actually reduce this to just 2-bit information based on these exclusive conditions. If you assign your reduced residue based on these conditions, you get this equivalence. So the first two, you would use it to round the exponent bits or the fraction bits. The last three, you use it to round the residue. So these 2 bits information give you sufficient information to round correctly. So after all these derivations, we also need to test our implementations. So for special Posit arithmetic, it is still back to this table. All the results should tally with the entry of this table. So maybe you can perform exhaustive tests, at least for small posit sizes, to test if you get the same answer. And to highlight that, you can also do negative tests. Let's say you are given any 2 normal posit numbers. They should not be returned any. They should never return any the special posit number, except for these 2 cases, that when A equal to minus B, and addition will return 0. The same for this, when A equal to B, subtraction will equal 0. Otherwise, all the other normal posit numbers will never return special posits. So for testing the normal posits, let's say you have you get posit implementation to test, and it produced a P result here. Since we can represent posit numbers with rational numbers exactly, including the result of division, we can represent exactly in a rational number. So we use rational numbers as a reference to compute, to perform the same operations and generate the exact value. So in this case, we have value V here and the computed P is here. So by inspection, you will find that this is obviously a wrong answer, but in a test, we need to do it systematically. So we look up the P plus and P minus, that is the nearest posit numbers around P. So if P is the correct answer, it should has the lowest error. But in this case, the P minus would have a lower error. So we know that P minus in fact is a better answer. And P definitely is not the correct answer. And in this case, you have a better posit implementation. The computed posit P is very near to your exact value V. And in this case, we need to determine if your implementation is rounding the exact value V correctly. So if you are rounding the exponent bits, then we use the metric error ratio. If you are rounding the fraction bits, we use the metric absolute difference. The correct answer should have the corresponding minimum error. In this case, the exact value is exactly at the midpoint of the two consecutive posit numbers. So we can check the least significant bit of posit P for 0, because in this case, we should round to even. For testing the encoding and decoding test, we can leverage the symmetry test. Whatever you encoded and you subsequently decoded, you should get back your inputs exactly. And posit bits, if you plus 1 to a posit binary bits, the value of the posit number should be strictly increasing. We know the intervals of the parameters in the formula, so we can arrange a multiple nested loops so that the next posit value is strictly increasing. So that means the expected posit bits should also be incremented over the iterations. So if you get a posit bit that is not incremented, then you know that is a wrong answer. As we doing more and more tests, we have more optimized implementation. The previous methods may deem to be too slow to be productive. So in this case, we can use a reliable implementation and generate the arithmetic input deterministically. We compute the results, and using the computed results, we generate the checksum. So in the future, as you update your implementations, you optimize it, you can do the same computation and just check with the checksum number. So you don't need to keep a large number of reference numbers. So in summary, I have presented the posit arithmetic based on fixed point, and a division may incur a residue that may not be exactly represented in a posit number. And I presented the conditions for posit rounding. The reduced residue with 2-bit information is sufficient for posit rounding, and also systematic software tests. So even we do not we do not mathematically prove all our computations, but at least we have very extensive software tests. And that's all from me. Thank you.
Thank you. We have a couple of minutes for questions.
Are the tests on, are they public? Are your tests on Posit Hub, or are you making them available?
So I start with Python implementations, and actually I spend a lot more time on generating the test cases, the routine to test. But just that the how we test it may not be updated as what I presented here.
But there is a public form of your test that people can access.
Yes, for the Python implementation, it is in my GitHub. That is also in the Posit Hub, the list.
Okay, so
Yeah, yeah.
Great.
Any other questions? Okay, well, let's thank the speaker again. Thank you.
Thank you.